Right now, the universe is dying. Not tomorrow, not in a billion years, but slowly, inexorably, with every passing second. Stars are burning out. Black holes are evaporating. Energy is spreading thinner and thinner across an ever-expanding void, and there is no way to stop it. This is entropy, the second law of thermodynamics, and it guarantees that eventually, in perhaps 10 to the power of 100 years, the universe will reach a state called heat death. No stars, no light, no warmth, no structure, no thought, just a cold, dark, infinite ocean of maximum entropy where nothing can ever happen again. Forever. Entropy is one of the most misunderstood concepts in all of science. People often call it disorder, which is vague and misleading. Entropy is better understood as the measure of how energy is distributed in a system. When energy is concentrated, like in a hot star or a tank of compressed gas, entropy is low. When energy is spread out evenly, like heat dissipated into empty space, entropy is high. The second law of thermodynamics states that in any closed system, entropy always increases over time. You can temporarily decrease entropy locally by adding energy from outside, but the total entropy of the universe always goes up. Always. This law is unlike any other in physics. Most physical laws are reversible. Drop a ball, and you can imagine the film playing backward. The ball rises. Collide two particles, and reversing their velocities makes the collision play in reverse. But entropy doesn't work that way. It has a direction, an arrow. When you burn a log, it turns into ash, smoke, and heat. You never see ash spontaneously reassemble into a log. When you drop an ice cube into hot coffee, it melts and the temperatures equalize. You never see the coffee spontaneously freeze part of itself to recreate the ice cube. Entropy increase gives time its direction. It's why you remember the past, but not the future. It's why things break, age, and decay. So why? Does entropy always increase? Because there are vastly more ways for energy to be spread out than concentrated. Imagine you have a deck of cards perfectly sorted by suit and rank. That's one specific arrangement, low entropy. Now shuffle the deck. There are trillions upon trillions of possible mixed-up arrangements. Almost all of them look random. The probability of shuffling back into perfect order is astronomically low. Similarly, the universe explores all possible arrangements of energy, and the overwhelming majority of those arrangements have high entropy. The universe isn't being malicious, it's just playing the odds, and the odds always favor disorder. At the beginning, the universe had extremely low entropy. Right after the Big Bang, all the energy in the universe was concentrated in an incredibly hot, dense state. That's a highly ordered low-entropy condition. As the universe expanded and cooled, gravity began to clump matter into stars and galaxies. That seems like it's creating order, reducing entropy. But it's not. When gas clouds collapse to form stars, they release enormous amounts of heat into space. That radiated energy increases the entropy of the universe far more than the local decrease from forming a star. Stars are entropy engines. They burn hydrogen, produce light and heat, and spread energy across the cosmos. Every star that shines is pushing the universe closer to maximum entropy. Over billions of years, stars exhaust their fuel. Smaller stars like our Sun will swell into red giants, shed their outer layers, and fade into white dwarfs, hot but slowly cooling embers. Larger stars explode as supernovae, scattering heavy elements into space and leaving behind neutron stars or black holes. Eventually, all stars will burn out. In about 100 trillion years, 10 to the 14 years, the last stars will die. The universe will enter what's called the Degenerate Era. No new stars will form because all the available hydrogen will have been used up. The universe will be populated by dead stellar remnants. white dwarfs, neutron stars, and black holes, all slowly radiating away their remaining heat. But even black holes aren't eternal. As we discussed in the Hawking radiation video, black holes evaporate. Through quantum effects at the event horizon, they emit particles and lose mass. For a stellar mass black hole, this process takes an unimaginably long time, on the order of 10 to the 67 years. For supermassive black holes at the centers of galaxies, it's even longer, 10 to the 100 years. But eventually, every black hole will evaporate completely. The universe will enter the black hole era, dominated by these slowly decaying monsters. And when the last black hole finally evaporates, the universe enters its final stage, the dark era. In the dark era, the universe contains only a thin soup of elementary particles, photons, neutrinos, electrons, positrons, spread across an ever-expanding void. The temperature approaches absolute zero. No structure remains, no stars, no planets, no atoms heavier than hydrogen. The expansion of space has stretched the universe to such a size that particles are separated by light years, then millions of light years, then distances larger than the observable universe today. Encounters between particles become vanishingly rare. Nothing interesting can happen. The universe has reached heat death, maximum entropy. At this point, the universe is in thermodynamic equilibrium. Every region has the same temperature, the same energy density, the same nothing. There are no gradients, no flows of energy, no differences that could drive processes or create structure. Time, in a meaningful sense, stops. Not because clocks stop ticking, photons still move, but because nothing changes. Every moment is identical to the last. An observer, if one could somehow exist, would see an eternal, unchanging darkness. But of course, no observers can exist. Life requires energy gradients. It requires stars to power chemistry, planets to host complexity, entropy differences to drive metabolism. In a universe at maximum entropy, life is thermodynamically impossible. This is the ultimate fate predicted by our best understanding of cosmology and thermodynamics. It's not a guess, it's a consequence of well-tested physical laws. The second law of thermodynamics has never been violated. Not once. Not even in quantum mechanics. Entropy always increases in closed systems, and the universe, by definition, is the ultimate closed system. There is no outside to inject fresh energy. The cosmic game is rigged. Entropy always wins. Some people find this depressing. If everything ends in heat death, what's the point? Why does anything matter if it's all going to dissolve into a featureless void? This is a fair emotional reaction, but it's also a philosophical question, not a scientific one. Physics describes what will happen. It doesn't prescribe what you should feel about it, or what meaning you should assign to your life. Meaning is something humans create, not something the universe provides. The fact that the universe will one day be cold and dark doesn't erase the warmth and light that exist now. The fact that you will die doesn't make your life meaningless. The same logic applies cosmically. There is also a strange beauty in the second law. Entropy is what allows change, growth, and complexity. A universe frozen in perfect order, low entropy forever, would be static. Nothing could happen. It's the flow from low to high entropy that powers every process in the universe, from the fusion in stars to the thoughts in your brain. Life exists because the universe is not yet at equilibrium. We are temporary patterns sustained by the flow of energy from hot to cold. We are ripples in the river of entropy, and when the river runs dry, the ripples disappear. But while they last, they are real. Another question arises. Could we survive heat death? Could advanced civilizations find a way to persist indefinitely, even as the universe approaches maximum entropy. Physicist Freeman Dyson explored this in the 1970s. He imagined a civilization that slows its metabolism to match the cooling universe. As the temperature drops, they think slower, hibernate longer, wake briefly to perform calculations, then sleep again. By carefully managing energy, they could theoretically stretch their existence indefinitely, subjectively experiencing infinite time even as the objective universe fades. But more recent research suggests this doesn't work. Quantum mechanics imposes limits. Even an idealized civilization would eventually run out of usable energy. There is no escape. The universe's death is final, unless something else happens. Some speculative theories suggest the universe might not end in heat death. If dark energy behaves differently than we think, the universe could recollapse in a big crunch or rip apart in a big rip. If the vacuum of space is metastable, it could undergo a phase transition. A bubble of true vacuum could nucleate and expand at the speed of light, obliterating everything in its path and resetting physical constants. If the multiverse is real, our universe is just one bubble in an eternal foam of creation and destruction. These possibilities are fascinating, but they're also speculative. Current evidence points toward endless expansion and heat death. There's also a philosophical angle, the Boltzmann brane paradox. If the universe lasts forever in a high entropy state, quantum fluctuations could, by sheer chance, briefly create pockets of low entropy. These fluctuations could randomly assemble complex structures, including branes. A Boltzmann brane is a disembodied self-aware mind that pops into existence by random chance, thinks a few thoughts, then dissipates back into chaos. If the universe lasts forever, Boltzmann branes are inevitable. In fact, they should vastly outnumber normal branes like yours that evolved in low-entropy environments. Statistically, you should be a Boltzmann brane. But if you are, then your memories, your knowledge of physics, everything you think you know about the universe is just a random hallucination. The theory eats itself. This is one reason physicists dislike eternal high-entropy futures. They produce absurd predictions. But no one has a clear resolution. The second law also raises questions about the beginning of the universe. If entropy always increases, and the universe started in a low-entropy state, where did that low entropy come from? Why did the universe begin in such an unlikely, ordered condition? This is the problem of initial conditions. Some cosmologists think it's explained by inflation, a rapid exponential expansion right after the Big Bang that smoothed out irregularities and set up a low-entropy start. But inflation itself requires specific initial conditions. Others appeal to quantum cosmology, where the universe tunnels into existence from nothing. But nothing is still a quantum state with properties. The origin of low entropy remains mysterious. One radical idea: the universe's low entropy start is just a statistical fluctuation in an eternally existing multiverse. Most of the multiverse is in equilibrium, but occasionally a region fluctuates into low entropy and begins expanding. We live in one such region because only low entropy regions can support life. This is an anthropic explanation. It doesn't tell us why the multiverse exists or why it has the properties it does, but it shifts the mystery up a level. Another question: does entropy apply to the universe as a whole? General relativity complicates things. In an expanding universe, the concept of entropy becomes subtle. You can't easily define a total energy for the whole universe because space itself is dynamic. Some cosmologists argue that the entropy of the universe has been increasing since the Big Bang and will continue until heat, death. Others point out that gravitational systems behave strangely. When you add energy, they can become more spread out, not less. Black holes have enormous entropy. The entropy of the observable universe is dominated by supermassive black holes. As the universe expands and black holes evaporate, does total entropy increase or decrease? The math gets complicated, but the consensus is that the second law still holds cosmologically. The universe is heading toward maximum entropy. Finally, there's an existential question. If we know the universe will die, should we care about the far future? Should we invest in space exploration, life extension, interstellar civilizations, if it's all doomed anyway? This is where values and timescales matter. Heat death is trillions of years away. Humanity has existed for a few 100,000 years. Recorded civilization is only a few thousand years old. Even if we survive for 1 billion years, far longer than any species ever has, we'll still be nowhere near the end. The universe is young. There is unimaginable time ahead. The fact that it ends eventually doesn't diminish what can be achieved in the meantime. Moreover, meaning doesn't require eternity. A song doesn't need to last forever to be beautiful. A life doesn't need to be infinite to be valuable. The same applies to civilizations, to life in the universe, to the universe itself. Entropy's victory is inevitable, but it's not yet. And in the space between now and then, there is room for everything that matters: discovery, connection, creation, love, understanding. The universe may be dying, but it's not dead, not even close. So when you hear about heat death, don't despair. Let it sharpen your appreciation for the present. Let it remind you that energy, structure, and complexity are gifts, not guarantees. The fact that stars shine, that planets form, that life emerges, that minds can contemplate entropy, all of this is temporary, and that's what makes it precious. The universe doesn't owe us forever. It's given us now. And for as long as now lasts, whether that's a human lifetime or 1 trillion years, there is work to do, beauty to witness, and meaning to create. Entropy will win in the end. But we get to decide what happens in the middle.